Welcome back, everybody. This is our first class in NEET previous year questions for chapter Atom of class 12th. Before this video, we have made several videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for JEE. So if some of your friends are preparing for JEE, then you can guide them through those videos. And with this, let's start today's video. And also, if you like to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount will be highly appreciated. With this, let's start today's video. Now, here we have the question number one, that when an alpha particle of mass m is moving with velocity v bombarded on a heavy nucleus charge Ze, its distance of the closest approach from the nucleus depend on ms. Now, as mentioned that alpha particle is moving with some velocity. So what will it have? It will have some kinetic energy that it will be in the form of half mv square. Now, suppose this is alpha particle and this is the nucleus. When this alpha particle reaches near to the nucleus, so what will happen? That its velocity will keep on decreasing, and after certain time it will stop for a very small moment of time. And this distance, when this is stopped, so the distance from the nucleus, that will be equal to let's say closest approach distance d. Now, again, we know that as for interatomic collisions, means for the collisions related to atomic type particles, there is energy is always conserved. So this kinetic energy half mv square will gets converted into terms of potential energy, and that will be equal to k times ze into charge of alpha particle, that is 4 times e, oh sorry, 2 times e, divided by the distance. So from this, what we can write, that here k is basically 1 by 4 pi epsilon no. So from this equation, we can write that t is inversely proportional to 1 by m, and that is option D for us. Now moving ahead, an alpha nucleus of energy half mv square bombarded on heavy nuclear Ze, the distance of closest approach for the alpha nucleus will be proportional to. Now we have to find out that whether it will be proportional to mass and velocity and these type of stuff. So we have already solved this in the previous one here, and let us write the formula again. That half mv square is equal to k times Ze into 2e by d. This term is basically potential energy. This is kinetic energy. Kinetic energy gets converted into potential energy. That's energy conservation here. So we have to find out distance. So what distance is proportional to? So if we write down the formula for distance only, then distance will be equal to 2k ze square, and this 2 gets also multiplied, so this will be 4k ze square divided by mv square. So what we have, that d is proportional to 1 by m, d is proportional to 1 by v square, and d is proportional to ze. So from the given options, we can say option A is wrong, option B is wrong, option C is right, and option D is right. Means here we have two options which are right. So I think there is some problems with the given options. In the next one, in the Rutherford scattering experiment, when a projectile charge Z1 and mass M1 approaches a target nucleus of charge Z2 and mass M2, distance of closest approach is R0, the energy of the projectile is. So we have to find out energy of the projectile. So basically, energy of the projectile is its kinetic energy, and we have already discussed that kinetic energy will be conserved in the form of potential energy, or we can write that half m1 into v1 square, that is the energy of charge particle m1 moving with some velocity v2 or v1, and that will be equal to k times charge of first particle is z1, charge of second particle is z2, divided by the distance that is r. So this will be the formula, and from this we can say this is the energy, and it is directly proportional to z1 z2 and inversely proportional to r naught. And here we have that is option B, that directly proportional to z1 z2. Moving ahead to the next one. The radius of the innermost orbit of hydrogen atom is 5.3 10 to the power minus 11 meter. What is the radius of third allowed orbit of the hydrogen atom? So we know that the radius for hydrogen atom varies like this, that Rn is equal to n squared times a naught. Now n is the we can say orbit number, and we have here it is equal to 3 for this case, and the value of a node is 53 angstrom, or that will be 9 into 53 10 raised to power minus 10. Oh, sorry, a correction here, this is not 53 angstrom, this is actually 0.53 angstrom. So what I can do, I can write it like 5.3 into 10 raised to power minus 11. Now when we solve this, we will get 47.7 10 raised to power minus 11, that will be 4.8 into 10 raised to power minus 10. So that becomes 4.8 angstrom, and that is nearest to option B for us. So moving to the next one. Let T1 and T2 be the energy of electron in the first and second excited state of hydrogen atom respectively. According to Bohr model, ratio we have to find out. So for the according to Bohr model, we know that En is equal to minus 13.6 by n square, where n is the principal quantum number for the orbit. So for the first orbit, E1 will be equal to minus 13.6 by 1 square, and for the second orbit it will be minus 13.6 divided by 2 square. And if we take the ratio, if we divide E1 by E2, then what we will get? We will get 4:1, I think. Yeah, it should be 4:1. Oh, let me read the question properly. That we have to find out for the excited states. This is not for the normal states. This is for the first and second excited state. So for the first excited state, n is equal to 2. And for the second excited state, n is equal to 3. So we have to calculate E3 here also. So E3 will be minus 13.6 by 3 square. Now, this is the first excited state, and that will be equal to T1. This is second excited state, this will be equal to T2. And now T1 by T2 will yield us 2 square by 3 square. That will be 9 by 4. So that is option D for us. Moving ahead. Total energy of the electron in n stationary orbit of the hydrogen atom can be obtained by minus 13.6 by n square electron volt, and here that is option B. For which of the following Bohr model is not valid? Singly ionized. So we know that Bohr model is only valid on hydrogen like atoms. Now, what do you mean by hydrogen like atoms? That which have only one electron in orbit. Why? Because if we have two electrons, let's say if we have two electrons, then they will interact with each other. And if they interact, then they have their own potential energy of interaction. We don't need that. That causes slight changes, and that is known as perturbation. So basically, you have to remember that when an atom have only one electron, only then hydrogen we can say Bohr model is going to applicable on it. So hydrogen atom, it will applicable singly ionized neon atom. deuterium atom, and singly ionized helium atom. Now, we know that helium atom has two proton and two electron. So if we ionize it, so what it will have? So it will have two proton and one electron, and it obeys the required condition that it should have only one electron. So singly ionized helium atom is going to obey it. Deuterium atom is basically hydrogen atom, so it is also going to orbit. Hydrogen atom obeys, so only we have only option C left, where we have neon. We know that neon has, I think, 10 electrons. So if we removed one electron, then it will still have 9 electrons left. And due to these 9 excess electrons, we cannot apply Bohr model on it. So option C is the right answer here. Moving ahead. The total energy of the electron in orbit is minus 3.4 electron volt. Its kinetic and potential energy are. So here it is not mentioned that regarding which of the system it is asked, but normally these type of questions are related to either hydrogen or hydrogen-like atoms. So here it is mentioned that total energy is minus 3.4 electron volt, and you can also solve this question from the gravitational chapter of the class 11th, where kinetic energy is basically modulus of total energy. So here kinetic energy will be positive 3.4 electron volt, and potential energy is basically twice of the total energy. So this will be minus 6.8 electron volt. And if we add both of these, we will get total energy that is negative 6.8. So kinetic will be positive and potential will be negative. So that is satisfied in option B. Now moving ahead. So in the ninth question, the radius of the first permitted Bohr orbit for the electron in a hydrogen atom is equal to 0.51 angstrom, and its ground state energy is given. If the electron of the hydrogen atom is replaced by the muon, charge is same and mass is 207 times mass of electron. The first orbit radius of the ground state energy will be. Now, if you remember the formula for radius, then we know that radius is inversely proportional to mass of electron. So let me write it ME, and energy is directly proportional to mass of electron in case of a hydrogen atom. Now, if electron is replaced by the muon, then what will happen? That radius of muon will be inversely proportional to mass of muon, and energy of muonic atom will be proportional to mass of muonic atom. So what we can do here, we can divide both of these. We can divide both of these equations, and what we will get, R by R of mu is equal to Me by Mu. So from this ratio is equal to 207. So radius of muon will be equal to radius of electron divided by 207. And that radius of electron is 0.51 angstrom. So 10 is power minus 10 divided by 207. And this will yield to 2.56 into 10 is to power minus 13. And that is given in option C and D. Now moving to the energy part. Now we know that energy, if we divide these two, what we will get? Energy for hydrogen atom normally, that is, let us say, minus 13.6, divided by the energy of muonic atom is equal to mass of electron by mass of muon, and this ratio will be equal to 1 by 207. So from this, energy of muonic atom will be minus 13.6 into 207. So when we solve this, we will get negative 2.8, and this is in electron volt, and our answer will be in kilo electron volt, 2.8 kilo electron volt. So that is given in option C. So option C is the right answer here. Moving ahead, the ratio of kinetic energy to the total energy of electron in Bohr orbit of the hydrogen atom is. So we have to find out ratio of kinetic to total energy. Now we know that relation between kinetic energy and total energy is that kinetic energy is modulus of total energy. So their ratio will be equal to, first we have kinetic, so ratio will be 1 ratio minus 1. And if in case of magnitude, it will be 1 ratio 1. So we will go with option B because our total energy is negative. If it has been mentioned that we have to consider only magnitude, then answer would be option C. Moving ahead. An electron in hydrogen atom makes a transition N1 to N2 where N1 and N2 are principal quantum numbers of the two states. Assuming Bohr's model to be valid, the time period of the electron in the initial state is 8 times that of the final state. The possible values of N1 and N2. So we know, as per mentioned here, that time period in one state is 8 times the time period of the other state. And we also know the relation that time period is proportional to NQ. And how we know that? We know that frequency of electron revolution is proportional to 1 by NQ. So time period will be inverse of frequency. So time period will be proportional to NQ. So from this we can write that N1 cube should be equal to 8 times N2 cube. And from this N1 is equal to 2 times of N2. Now for to solve this, let's say N1 is 1, then N2 will be 2. Or let's examine the options. In case of N1 is 6, then N2, from this N2 will be N1 by 2. So N2 will be 3. So option A is rejected. If N1 is 8, then N2 will be 4. B is rejected. Option C, and N1 is 8, then N2 will be 4. Then option C is rejected. Only option D is left. So that will be the right answer. Moving ahead. An electron of stationary hydrogen atom passes from the fifth energy level to the ground state. The velocity of the atom of mass m required as resultant of photon emission will be. Now, what is happening here? That there is a transition from the fifth level to the ground state. Now, during this transition, what we will get? We will get a photon and plus electron in ground state. So these are the final, we can say, this is our final setup. Now we know that momentum carried by a photon is equal to h by lambda. And initially, when this electron jumps from the fifth state to the ground state, we assume that it was in the fifth state, it was initially at rest. And when it goes to the first state, there was some momentum carried by the photon, and we know that total momentum, P, will be conserved. So momentum carried by the photon will be equal in opposite to the momentum carried by the electron. And how we can calculate momentum carried by the photon? That it will be h by lambda. So we need lambda for to calculate the momentum photon. And how we can calculate lambda? We know that transition is happening. And for this type of transition, we can write that 1 by lambda p will be equal to Rydberg constants times r, because happening in hydrogen atom, 1 by 1 square minus 1 by 5 square. So from this, we can say that 1 by lambda p will be equal to r into 1 by 1 minus 1 by 25. And from this lambda p, we can solve it 25, and here we will get 24. And here we have r, and this is 1 by lambda p. So momentum carried by the photon pp will be equal to h by lambda. So that will be at 24 hr divided by 25. Now this will be the same momentum in opposite direction will be carried by the electron. So for electron, momentum will be, as it is a particle, so mass into velocity should be equal to 24 hr by 25. And from this, velocity of electron at least should be 24 RH by 25 ME. And here we have assumed that initially electron was uh, in the fifth state, electron was in rest. Using that assumption, we have solved this. Okay. So that will be 24 HR by 25 Me. That is option A for us. Moving ahead, the energy of the hydrogen atom in the ground state is minus 13.6 electron volt. Energy of the helium ion in the first excited state will be. Now, for hydrogen like atoms, we know that En is equal to minus Z square into 13.6 electron volt by N square, where N is the orbital number of that hydrogen like atom. So for here Z is the basically atomic mass. So for He positive, it has atomic mass as 2. So minus of 2 square into 13.6 electron volt. Now divided by the first excited state. Now for first excited state, N is equal to 2. So divided by 2 square. Now 2 square gets cancelled and the answer will be minus 13.6 electron volt. So basically, first excited state is for He positive ion is equivalent to the ground state of hydrogen atom. Moving ahead, the electron in the hydrogen atom jumps from excited state N3 to ground state N1. Then the photons thus emitted irradiate photosensitive material. If the work function of the material is 5.1 electron volt, stopping potential estimated to be. So we have to calculate the stopping potential. For that, what we need the energy of the photon which strikes this material. So, and how we can calculate energy? Energy can be calculated by the finding out the difference in the energy levels. So this is happening in hydrogen atom from the N3 to N1 state. So for E3, that for N3, energy will be minus 13.6 by 3 square, that is 9 electron volt. And this will be equal to minus 1.51 electron volt. And for the ground level, E1 will be equal to minus 13.6 electron volt. So the transition energy, the energy of the photon will be equal to minus 13.6 plus 1.51, as it is negative and negative. So that's we get positive, or basically the difference, and take magnitude of it. That will be 12.1 electron. So this is the energy of the emitted photon. Now work function of the material is 5.1 electron volt. So the energy of the emitted electron, that is kinetic energy maximum, and that is also equal to an E times the stopping potential EBS, will be equal to 12.1 minus 5.1, that will be 7 electron volt. So from this, stopping potential will be 7 volt. That is option D for us. Moving ahead, the ionization energy of the electron in the hydrogen atom in its ground state is 13.6 electron volt. The atoms are excited to higher energy level to emit radiation of 6 wavelengths. Maximum wavelength will be. So we have to find out that what will be the maximum wavelength. Now, as mentioned that we have 6 wavelengths here. So for wavelengths or the number of radiation emitted, we have a relation that n into n minus 1 by 2. This is the number of radiation emitted, and number of radiation are here 6. So from this, n into n minus 1 is equal to 12. If we substitute n is equal to 4, then we will get 4 into 3 is equal to 12. So answer is n is equal to 4. So means transition is happening from the fourth level uh, and between the lower levels 4 to 3 to 2 to 1, and that is basically ground state. So this needs need to be here. So here we are getting the transitions. Now, as mentioned that we need maximum wavelength. So lambda need to be maximum, and if lambda needs to be maximum, then frequency needs to be minimum. And if frequency needs to be minimum, means energy difference needs to be minimum. And where will we get minimum energy difference? We will get between the two closely spaced levels, and we know for the first level energy is minus 13.6 electron volt. For second level it is something 3.4, I think. For the third we just solved it, it was 1.51, and for the fourth I think it is 0.85. You can calculate the exact values, and you will find that minimum energy level or minimum energy difference will be the highest between the highest level, that is 4 and 3. So option D will be the right answer. Now with this, we end this video here. Hopefully what we covered here is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. Like these videos, then do share them, and like to support us, do scan these QR codes and donate us with whatever amount you want. Thanks for watching, and we will meet in next video.